Okay. Hi, everyone. Thank you for coming. Today we have Jaromir Sant, who's a PhD at Warwick, and he'll talk about inference of natural selection from allele frequency time series data using exact simulation techniques. Please go on.
Cool. Thanks. Thank you for tuning in. So this is some work that we've done with Posterior and Dario. I believe they're in the audience. I should pretty much emphasize that this is still work in progress. We're just quite keen to get this out and to present it to you guys. And it deals with the problem of inferring natural selection from these allele frequency time series data. And in particular, we'll be using some exact simulation techniques to do that. The standard approach in population genetics has always been to use sort of modern day data to inform yourself about selection, and that's quite restrictive in the sense that using data from the current population is only giving you access to data that's from a kind of a static snapshot of the population, and stuff like selection is acting on the population over a very wider span of time. So actually you should expect to do much better once you incorporate this temporal dynamics into it. And this is what we're trying to do over here, because as I'm sure most of you know, there have been some recent technological advances in gene sequencing, and coupled with the fact that archaeologists are now becoming more and more able to extract DNA from fossils and remains in burial sites and so on. This has given rise to sort of these allele frequency time series, where I should say that aDNA just means to the fact that it's ancient DNA, so it's DNA coming from fossils. And as you can see over here, I have a data set that is the Ludwig et al. 2009 data set relating to horses, and it spans back quite a number of years, because the first time points are sort of 13,000 years before Christ, so that's roughly 15,000 years ago. And what these square points here are just sort of samples that archaeologists have found dating from different times and from presumably different sites, and based on the counts they find in these archaeological sites, they estimate the frequency of the allele in the population, and then they get these data sets from there. And one curious fact is the fact that horses can go this far back in time because they're one of the few organisms, one of the few animals that actually managed to survive the severe and drastic changes in climate that happened over the millennia. So they're one of the few animals that we can trace back to quite a long time, and this means that we're going to have a sort of a longer time series. And I'd point out the fact that the time series here is in the range of thousands of years. If we look at another time series, which is from the Mathies and McVean 2013 paper, and this is dealing with the peppered moth, then the time frames is just 50 years. And in this particular study, the authors were interested in sort of estimating selection whilst accounting for geographical location of the data points from where they're coming. So in this case, we have the map of the UK on the left-hand side, and each sort of red square grid here corresponds with another grid here on the right-hand side. And you can see that they're split based on sort of the geographical region, and for each one, they've tried to estimate the selection coefficient. So that's one other example. And the last one I have is the one coming from Bolbach et al. From 2008, which is actually using data from Hummel et al. 2005. And this is time series data for the CCR5 delta 32 protein in humans. And as you can see, there's sort of a remain that's dating back to roughly 1,000 years ago, and then more recent estimates from burial sites. I believe these were from medieval Germany, and you can get this sort of reading here, which corresponds to the present day. So that would presumably be something like the population, the inferred current population value over there. So these things have started cropping up fairly recently. That's because of these increases in the gene sequencing and aDNA extraction. However, one feature that is quite specific to this case is that we only have very few data points. Right here we only have 5, and the previous one we had slightly more because they're more recent. But the fact is that this is not sort of the usual big data setting where we have lots of data points and we somehow need to find a computationally efficient way to infer the parameters. In this case, we want to develop techniques that can take in very little, or rather a restricted amount of data, and extract as much as we can from that to infer the parameters. So this is what we're, this is sort of the setting we're starting out from, and this is a brief sort of rundown of all the literature that is on the topic in the past couple of years. And as you can see, it sort of started in 2008 and then picked up from there. And from this list, I'll perhaps highlight these three papers because they're the first sort of formally setting the scene mathematically. And all three are sort of based on a discretization of some sort of the quantities involved. And I'll try and make this a bit more clear going forward. And another three papers that I will sort of outline over here are these three over here, and they take a more sort of exact inference approach. And the thing with exact inference is that you need to choose the right reference measure to look at and to sort of use as a candidate. And in Schreiber et al., they kind of use the Bessel process for this. And the reason behind this is that the Wright-Fisher diffusion, that is sort of the gold standard in modeling allele frequencies in genetics, has two boundaries at 0 and at 1. And the Bessel process has a sort of similar, well, not sort of, it has a similar behavior at the 0 boundary, which would make it sort of a nice candidate for that. The only problem is that the Bessel process doesn't have a boundary at 1. So ultimately, there are some problems with the approach here in the sense that they couldn't fully extend the exact inferential scheme there, and ultimately had to rely on Riemann sums to deal with the integrals involved because they're path integrals. A similar approach was the one in the Gonsalves et al. 2017 paper, where instead they used Brownian motion, in particular the EA3 construction, which kind of is this layered Brownian motion simulation, which gives you also access to the maximum and the minimum of any Brownian bridges you simulate. And that all sort of automatically implies that if your maximum or minimum exits your state space 0, 1, then you can just simply discard the proposal, which just means that it's going to be quite inefficient once you get close to the boundary 0 or 1. But then they use the Barker step to deal with the fact that the likelihood introduced then is going to be an intractable quantity, which you cannot really evaluate in any way because your reference measure doesn't account for the fact that you have boundaries. And finally, I'll briefly mention the Kwon-Kam-King paper from 2020. And this does exact inference, but it's looking at the problem from the filtering perspective. So it's somewhat separate to what we're going to be presenting over here. OK, so let me describe a bit the modeling and observation dynamics that we have. So as I said, the gold standard is to use this Wright-Fisher diffusion. And there are three main terms over here. We have the selection term coming up over there in the drift, the mutation terms, which are going to be ensuring that our diffusion remains in 0, 1. And then we have what's called genetic drift, which is just the square root of x into 1 minus x. So this is going to be the process that is going to be sort of driving our underlying mechanics. But what we want to do is to conduct a Bayesian inference on this parameter sigma based on noisy observations which are coming from this Wright-Fisher diffusion, which are driven by this Wright-Fisher diffusion. And the way to look at it is that we have this underlying diffusion x, which is this gray path over here. And at a sampling time, the true value of xt is little x, and then we sample, we model the observations yti as being binomial draws with the probability parameter given by the Wright-Fisher diffusion, and the sample size being known. And this is sort of just the fact that an archaeologist knows how many samples he has, right? So what sort of random is this xti over there? So this is sort of the modeling framework we're working. And perhaps just the standard way to approach this would be to just marginalize over the unknown path x, right? It's saying I'm having bad network quality. Can you still hear me?
Yeah, we can. You just dropped out for half a second, but otherwise you're fine.
Okay. Right.
Maybe
so
you can.
The standard Bayesian approach.
Sorry. Maybe you can turn off the camera, and then I think that then.
Yeah, sure. Okay. Cool. Maybe that'll be better. Okay. Right. So the standard Bayesian approach would be to just take the usual posterior, decompose this, look at the likelihood, and then just marginalize over the values of the right Fisher diffusion. And then you just need to weight these by the transition densities of the said diffusion. But this is where the problem sort of crops up, because as is the case with most diffusions, we don't have an analytic form for this transition density. This is where Bolbach et al. Applied a discretization. They numerically solved the Kolmogorov backward equation for this, and then plug that in and sort of work forwards from there. A nice paper from the one I highlighted earlier was the Steinrücken one, where they actually find an eigenfunction decomposition for this transition density, and then show that this can be sort of written down in a nice matrix multiplication form. But of course, you're dealing with eigenfunctions, and so this means that the matrices involved are going to become these infinite dimensional creatures. And if you want to evaluate them, as you're going to have to do at some point, well, then you're going to have to truncate, because they're sort of these infinite matrices. Okay, but is there something that we could glean if we just incorporated the latent path as an additional variable in our state space X? And the short answer is no, because ultimately all that changes is the fact that we're now going to have a product of transition densities there. And we don't really know how to work with these anyway, because we don't have an analytic form for them. So at this point, we just entertain the idea of like, okay, what happens if we just discretize and use some kind of an Euler-Maruyama scheme to generate these points X? And actually, there's a couple of problems there which make it not quite so nice. The first and foremost one is that a discretization is immediately going to imply some kind of bias on our results, on our output. And of course, you could argue that you could take a finer discretization, and then if you formally prove that your finer discretization is converging towards the right thing, then you're going to retrieve the truth to some extent. But that just means that you're going to have to pay a hefty computational cost increase, right? So perhaps that's not quite so nice to do. And moreover, the Euler-Maruyama scheme is not quite suited for simulating the right Fisher. There's no mechanism in the Euler-Maruyama scheme, in the sort of vanilla one, that allows you to account for boundary behavior. And yes, there are schemes that are sort of Euler-Maruyama that allow for reflective proposals, but this would just sort of add on to this computational overhead that you already have incurred from using a finer discretization. And something you cannot sort of fix by using these reflecting Euler-Maruyama proposals is the fact that you should actually be targeting X given your data and the parameter, not just X given the parameter, because otherwise there's some information in the data that you're not really sort of utilizing to its full extent. Okay, so this slide was mostly there just to sort of motivate why discretization perhaps is not quite as nice as it might seem. And so we approached this problem by saying, okay, can we get something from this that would use exact simulation that would help us in dealing with this intractable quantity? So perhaps the best way to explain this is to look where we are in terms of exact simulation for the right Fisher, right? And to do this, we just start with a neutral right Fisher transition density. So now we just need to care about, so now sigma is just set to 0, right? And we know that, so this is a classical result in population genetics, that you can kind of write down this transition density as this infinite series form over here. And what crops up quite immediately is that this factorization could give rise to some form of a hierarchical simulation, provided that I can draw from this QM of t, which is actually this known time-dependent mixture distribution on it. And this is the work that sort of Paul and Dario did in 2017 when they showed that you could actually get draws from this p0 theta of txy exactly. And it's quite a nice, neat result, because you just simulate your m from this QM of t, then conditional on the value this m takes, you draw a binomial, And then conditional on both this M and this binomial draw, you just draw a beta density, and you're assured that you are sort of drawing a sample from this neutral transition density. And I should perhaps point out here that this QM of T is actually intimately linked with the Kingman coalescent, because it turns out that it is, so QM of T is the probability that starting from infinity, your Kingman coalescent is now has, so the ancestral process now has M lineages left after a time T. Okay, so this is how to deal with the neutral case, but we're interested in the non-neutral one. So what can we do there? And to tackle this, we need to look at sort of some form of a rejection sampler scheme, which is what I'll be explaining now. So if we start with WF0, which is just a probability measure for a neutral path, and WF sigma to be the probability measure for a non-neutral one. A classical result is that we have absolute continuity of these two measures. And furthermore, we can just use Gurzanov's formula to derive the Radon-Nikodym derivative, which is given by this functional form over here. And what's particularly nice of this in our case is the fact that both A and phi sigma are known polynomials, so we can bound them easily. And based on this, and the fact that this sort of integral over here is problematic because it's a path integral, we can kind of appeal to the idea of exact simulation that Beskos and Roberts developed in the mid-2000s to relate this to the probability of a Poisson point process. So, as I said, we can bound this phi sigma from below by, say, phi sigma minus. And the key observation here is that this right-hand side is the probability of an event we can simulate with finite computation. So if we generate a Poisson point process of unit rate on the time interval 0t and on this interval 0 phi sigma plus minus phi sigma minus, then the probability that this process has no points underneath the graph mapping t into phi sigma of xt minus phi sigma minus is precisely equal to this exponential term over here. And the only extra term we need to account for is this e to the a of xt, which we can just pass as a sort of e to the axt coin flip. So this is just a recipe to allow us to simulate from the non-neutral Wright-Fisher diffusion. And actually, if we do embed this rejection sampler into MCMC scheme, we might solve the problem we had to start with. And this is sort of what Sarmaidis et al. Did in their 2013 paper. But there was the sort of idea there is to extend the exact algorithm for Brownian motion into an MCMC scheme to do exact inference. Okay, but if we're going to sort of add on this extra augmentation where we include what I shall call the skeleton points, we need to also calculate the contribution this will have to the likelihood. And to sort of illustrate this, I'm just going to consider the case when we have two observation points at time 0 and at time t, and I'll fix my Wright-Fisher diffusion to take the value little x at time 0 and little y at time t. And based on those two observations, I'm going to generate a unit rate Poisson point process phi on the time interval 0t cross 0 lambda sigma, where lambda sigma is just my difference between the maximum and minimum of phi sigma. And I'm going to let boldface omega denote the draws from the Wright-Fisher at the timestamps given by this psi, by the uniform marks on 0t given from the Poisson point process. And actually, I can derive the joint density of phi and omega conditional on them being accepted as being draws from the non-neutral Wright-Fisher. And this joint density is actually given by two different quantities. This exponential and lambda sigma to the kappa over here is simply the Radon-Nikodym derivative of phi with respect to a unit rate Poisson point process on 0t cross 0, 1. So we get this form over here. And the second term over here is just the Radon-Nikodym derivative of our proposal omega with respect to the law of the Wright-Fisher we're targeting, which is this. And the only annoying thing is that we're now going to have the presence of this a of t var theta xy which is this path integral, which, to complicate matters, is also an expectation with respect to function space, so to speak. But the underlying problem here is another one. It's the fact that our dominating measure actually depends on the endpoints x and y, because I've fixed these to start with, and I've already said that I'm going to be including my x as part of the state space. And if I'm going to use just a sort of a Gibbs sampler there, the problem is I'm not guaranteed absolute continuity of my measures. In fact, they're going to be actually mutually singular. So my Markov chain is not going to mix at all, and it's just going to be stuck in the support of one of the measures there. So what can I do to sort of decouple my dominating measure from x and y? And if you look at what they've done in sort of the Brownian motion case, where there you can appeal to translation invariance of the Brownian bridges you're simulating, and sort of just add and subtract the right quantities to lead to the fact that you just need to simulate Brownian bridges starting and ending at 0. But of course, we can't really replicate this in our case because we don't have sort of as nice a building block as the Brownian motion, in the sense that we don't have something that is translation invariant in our case. What we're doing is we're simulating from the neutral Wright-Fisher diffusion. So perhaps what we could do is we could change measure by using these Radon-Nikodym derivatives. But if we want to do that, we need something that's going to be absolutely continuous with respect to the Wright-Fisher. And the Wright-Fisher having two boundaries is going to be quite hard to find a process that actually has this type of behavior to start with. So perhaps we could just use another Wright-Fisher in itself, which might help us to this end. So this is what we're going to do now. And the thing is, we need to apply it twice. One to decouple the dependence on y, which is what we're doing over here. So we're just taking the law of the Wright-Fisher bridge going from x to y in time t, and finding what the Radon-Nikodym derivative is of this with respect to the law of a Wright-Fisher diffusion started at x. And that's just the inverse of the transition of the neutral transition density. And we also need to decouple the dependence on this x. And in this case, what we do is we find the Radon-Nikodym derivative between the laws of the diffusion processes when one is started from a fixed point x and the other one is started from stationarity. And in this case, it's just going to be a contribution of 1 over the invariant density f0 theta of x. Okay, so this is quite nice because all we need to do now is run everything as was before and then factor in these Radon-Nikodym derivatives over here. And if I do that now, the likelihood contribution from my skeleton points, which are these points S of omega, where all I've done is I've taken the timestamps from my Poisson point process and stuck to them the draws from omega at the timestamps. Then the density of these guys, simply given by this expression over here, and now our dominating measure is independent of the parameters we want to do inference on. So we're actually guaranteed that now our Markov chain is going to be mixing because we have absolute continuity of the measures that we're using as dominating measures. Okay, cool. So the dominating measure is independent of the latent diffusion values, but there is a problem because, as I said, this A of t var theta xy is still untractable. But actually, it's a good thing it's there because if you recall, we're going to have this product of transition densities. So this will be from xi minus 1 to xi and so on, and we'll have a product over these. But then, because we can decompose our non-neutral transition density into a neutral one, a term we know how to compute exactly, and this nasty A of t var theta xy, this guy is going to cancel out with this guy, and we're going to be happy because now our joint posterior over sigma, the skeleton points, and x, given the observations y, is given by the quantity here on the right-hand side. And we're guaranteed that our dominating measure is independent of the parameters we're doing inference on. There's only one problem, though, and that's the fact that we still have the presence of these neutral transition densities in the posterior, and the fact that these are an infinite series, so we can't really evaluate these at any point. And they're going to be particularly problematic when we're going to be computing what the acceptance probabilities are. And to make matters worse, you could say, well, can't you just, if you know how to simulate from this, can't you just use it as a proposal? And that would work for the interior points. But as soon as you want to update your xt0 or your xtn, then you're in a bit of a soup, because you have to deal with the fact that they're appearing both in the numerator and denominator. So that's also not quite clear how you'd go about doing that. But OK, so the problem is these neutral transition densities. And if you recall, we had this decomposition, this infinite series representation for them. And what we said was that we could actually simulate from this hierarchically. So perhaps if we just store this MNL and add them as extra things to look at and augment our state space with MNL, we could recover something that is workable. And if we do that, now we have a joint posterior density that's not only over sigma s and x, but also MNL. And this allows us to rewrite the transition densities we had previously in terms of these products here, where now we just have a contribution, which is the binomial PMF and a beta density, which are two things we're happy to see because we know how to work with, and everything is very nice. However, we have these QM thetas turning up. And these could be a problem. At the start, you might think that this might be a problem because actually these guys are written as an infinite series, but we know how to simulate from these exactly. And now we could entertain the idea of using these QMs as our proposals for the M values we're going to get. And this is precisely what we do. So we'll now set up a Gibbs sampler. We're sequentially going to update sigma, conditional on x, s, and this should read also MNL. Via Metropolis Hastings step, we're going to update our skeleton points using the exact algorithm, conditional on everything else. And then we're going to update these XMLs conditional on sigma s via Metropolis Hastings step again. And if we have a look at the proposal we're going to use, it's actually Gaussian proposals that will work for sigma. So they're going to be normal centered at the previous value with a standard deviation of 10. And the standard deviation of 10 there is simply down to the sort of results we got from simulations, which seem to imply that 10 gave good mixing. We also have to get proposals for these MNLs, and this is just going to be in the same way we had it for the exact simulation. We're going to draw our MIs according to this QM theta, and conditional on that, draw an LI, which is going to be a binomial draw. And then we're going to be using informed beta proposals for XTI. And when I say informed, I just mean that now we're reflecting the data into our proposal distribution over there. Right, and this is all nice because our posterior we can compute exactly, and we know we can sort of perform all of this nicely, provided that our proposals are nice enough to work with, which is what we've set up over here. What we've done is we've simulated some data, and because we have access to the exact simulation techniques, then we can simulate data which is following the dynamics of a Wright-Fisher process exactly, and then use this data and feed it back into the MCMC scheme to get an idea of how well this is, of how well our method is performing. And in this particular case, I'm setting my selection parameter to be 10. I'm taking symmetric mutation rates of a half at each boundary. My time increment is going to be 0.1. I'm going to start from a value of 0.1 for my initial point. And at each sampling time ti, I'm going to assume that there is roughly 20 samples on which the binomial draws are going to be drawn. And the choice of 20 here reflects the fact that usually if you look at the data coming from the archaeology and from these ADNA data sets, they usually have roughly 20 counts at each observation time. Right, and then the plot here is just giving us the exact draws, which are these blue circles, and then the red crosses are the binomial sampling based on the blue circles we had there. we look at the posterior we get, then the left-hand side is trying to illustrate the posterior plotted over the likelihood, prior, and truth. So this full red line over here is our prior. The circles here are the likelihood. I'll go into the color coding in a minute. The posterior is this kernel, so this black line is the kernel smoothed posterior, and this pink line is the true value of sigma. And the reason the likelihood is color coded is reflecting the fact that the different colors represent the fact that we have a different number of Poisson points. So these blue circles over here are the ones where no Poisson points were created. The orange ones are the ones where one Poisson point was created. The yellow ones are for 2, and so on and so forth. And the reason why you can kind of see that it's sort of shifting towards the right-hand side, the more the Poisson points there are, is the reason that the Poisson intensity increases as soon as the selection parameter increases. So the further right you go, the more Poisson points you get, and it feeds into that like that. Yeah, and on the right-hand side, we have a trace plot for sigma, and the acceptance probability is roughly 0.387, which is relatively acceptable, I would say. And the prior we fitted here was a normal 0.10. We just chose this so that it's sort of diffuse enough not to preclude areas of the parameter space. Right, but this is just the posterior for sigma. What does the posterior for the latent diffusion points look like? And on the plot on the left-hand side, I have the acceptance probabilities for each observation. So these blue circles are the observations, and the acceptance probabilities are the red crosses. As you can see, the acceptance probabilities are quite high, roughly in the range of 0.9, which is a bit too high. But I should point out here that we have found some bugs with the code, so this might explain what we're seeing here. I should also say that we have assumed that the prior on our initial point xt0 is uniform 0,1, which is a bit unrealistic, because if you think a bit, the sort of data sets that are highlighted by geneticists having selection acting on them will be the ones that start at low values and then end up at some high value, which is sort of like the plots we saw at the very beginning of the presentation. Or they'd be at very high values and then go to very low values, because this is sort of where you expect selection to sort of show up. This is where there is signal for selection. And in our case, we just assume that this is going to be uniform. So this is a bit unrealistic, and rather we should be looking at distributions which sort of assign more mass to the lower values over there. Yeah, so this is something we're currently looking at and would like to fix in this sense. Okay, so this kind of brings me to the end of my talk. So in summary, we've developed an MCMC algorithm that targets the exact posterior of the selection parameter sigma, and we've managed to do this via state space augmentation and using the exact algorithm for the right Fisher. And this immediately means that we don't need any kind of discretization, and we're guaranteed that our posterior draws are coming from the true posterior distribution. We've implemented this method in C++. As I said, there's a couple of bugs which we hope to resolve soon. But the results for the simulated data set are quite encouraging, and we plan to sort of run this on the Ludwig et al. Horse coat coloration ADNA data set. And the reason we picked up this one is because it's most of the mathematical techniques that have been developed over the past couple of years have sort of always been looking at this data set, and so it offers sort of a nice benchmark with which to compare our results. And some future work that I'd like to sort of just highlight briefly is the fact that we'd like to extend this analysis to incorporate other genetically relevant parameters, right? In the simulations, for instance, we set the mutation rates to a half, and if we want to apply our technique to the mutation rates, if we want to apply our technique to the horse's data set, then then to apply our method, we need to fix the mutation rates to something that is known a priori. And in particular, it's interesting because there are no estimates for the mutation rates for horses. And what they have done in previous studies, in the mathematical studies, was that they just used the values for humans. And you might argue that you wouldn't expect them to vary that much, but there is no reason a priori for them to be similar to humans anyway. And it would be nicer if you could develop an inferential framework which would sort of give you joint estimates of sigma and the θ1 and θ2. And then there's also including stuff like the allele age and effective population size, which would be genetically relevant quantities to look at as well. But including this, there's a bit of a problem here, because you now will be inferring 3 different parameters, and different configurations of these parameters could give rise to data which looks roughly the same. And if you have a look at the plot here on the left-hand side, try to illustrate this by plotting the stationary distribution of right Fisher diffusion when the mutation parameters are 10 and 4 and there's no selection. So this is just a beta distribution. Its parameters 10 and 4. But then you can kind of get a similar curve if you set the mutation rates both to be equal to 4 and take selection to be 4.5. And if you just feed this into the MCMC algorithm, it's going to be very hard for the algorithm to tell these two regimes apart and make a decision which one is the most likely. And what could happen is that you're going to keep on sort of migrating from one regime to another in your results. And one way you could fix this is to sort of first conduct another study which targets the mutation rates, use that to get more informative priors about your mutation rates, and then this would help the MCMC technique to decide which one of the 2 regimes you should be looking at. The second consideration, which is a bit more theoretical in nature, is the fact that we need to make sure that our dominating measure is not going to depend on any of the parameters that we want to do inference on. So as I showed earlier on, we went to a number of calculations to make sure that this was independent of the endpoints x and y, but the dependence on theta is still there over here. And if we want to include something like the effective population size, that inherently is going to change the observation time intervals Tn minus T0 by scaling it by a factor of 1 over whatever the effective population size is. So you need to find sort of a dominating measure which would decouple this dependence, but at the same time you need to retain absolute continuity so that your Markov chain will mix. And I think that's all I had to say. Thanks for tuning in.